Implementation of NASA's Nuclear Thermal Propulsion (NTP) engine by Q4 2025. Overview. NASA's Nuclear Thermal Propulsion (NTP) engine initiative is a pioneering project set to revolutionize space travel and exploration. The project aims for completion by the fourth quarter of 2025 and is structured around 5 critical phases: design validation, prototype development, testing, and safety assessments. A budget of $10 million has been allocated for these phases, underscoring NASA's commitment to ensuring the safe and effective deployment of this advanced propulsion technology. The NTP engine's development is anticipated to significantly enhance mission capabilities for deep space exploration, including potential missions to Mars. Key phases of implementation. 1. Design validation. Timeline: Q1 2023, Q3 2023. Objective: the initial phase focuses on validating the theoretical designs of the NTP system. This includes assessing whether the proposed designs align with practical capabilities and safety standards. Activities: engineers and scientists will conduct simulations, analyze materials, and refine designs based on analytical data. This phase is critical to identifying potential design flaws early in the process. 2. Prototype development. Timeline: Q2 2024. Objective: following successful design validation, the next phase involves the creation of physical prototypes of the NTP engine. Activities: this phase will include the manufacturing of engine components, assembly of prototypes, and preparation for testing. Lessons learned during design validation will guide modifications and improvements to the prototypes. 3. Testing phase. Timeline: Q4 2024. Objective: the testing phase will rigorously evaluate the performance and safety of the NTP prototypes under various operational conditions. Activities: tests will measure propulsion efficiency, thermal dynamics, and structural integrity. Data collected during this phase will inform any necessary adjustments to the engine before final deployment. 4. Safety assessments. Timeline: Q2 2025. Objective: concurrently with testing, comprehensive safety assessments will be conducted to ensure compliance with federal regulations regarding nuclear safety and operational standards. Activities: this includes risk analysis, environmental impact assessments, and evaluation of safety protocols. Close collaboration with regulatory bodies will be essential to address any safety concerns. 5. Final review and deployment. Timeline: Q4 2025. Objective: the final phase will involve a thorough review of all testing and safety assessment data before the NTP engine is deemed ready for operational deployment. Activities: final adjustments based on test results will be made, and then the NTP engine will be integrated into future missions aimed at deeper space exploration. Budget allocation. The implementation of the NTP engine is supported by a budget allocation of $10 million. This funding will be distributed across the 5 key phases, emphasizing the importance of thorough research, development, and safety assessments. The budget will cover research and development costs associated with design validation and prototype manufacturing, resources required for extensive testing of engine prototypes, safety evaluation processes to ensure compliance with nuclear safety standards. Strategic importance. The development of the NTP engine aligns with NASA's broader strategic goals to advance propulsion technologies for deep space missions. The NTP system offers several advantages over conventional chemical rockets, including higher specific impulse. The NTP system is expected to provide a significantly higher specific impulse compared to traditional propulsion methods, allowing spacecraft to achieve greater speeds and greater payload capacities. Reduced travel times. NTP technology could potentially cut travel times to destinations like Mars from several months to a matter of weeks, enabling more ambitious exploration missions. Enhanced mission flexibility. The increased efficiency of NTP allows for more complex mission profiles, including crewed missions to distant planets and potential human settlement initiatives. Integration of advanced technologies. The NTP initiative represents a significant leap in propulsion technology, incorporating advancements in materials science, nuclear engineering, and aerospace design. Key technological considerations include material selection. High-temperature resistant materials will be essential for the construction of the NTP engine, ensuring it can withstand the extreme conditions of space travel. Nuclear safety protocols. The project will adhere to strict safety regulations governing the use of nuclear technology in space, addressing public concerns about the deployment of nuclear propulsion systems. Challenges and considerations. While the NTP project presents exciting possibilities for the future of space exploration, several challenges must be addressed. Public perception and regulatory hurdles. Engaging with the public and regulatory bodies to build confidence in the safety of nuclear propulsion will be crucial. Technological risks. The complexity of developing a nuclear thermal propulsion system carries inherent risks that must be carefully managed throughout the project lifecycle. Budget constraints. Ensuring that the $10 million budget is effectively allocated across all phases will be essential to avoid delays and ensure timely completion. Conclusion. NASA's Nuclear Thermal Propulsion Initiative is poised to significantly impact the future of space exploration. With a clear timeline, budget, and strategic objectives, the project aims to develop a transformative propulsion system capable of facilitating deeper exploration of our solar system. By adhering to rigorous safety assessments and incorporating advanced technologies, NASA is committed to ensuring the successful implementation of the NTP engine by Q4 2025, ultimately paving the way for more ambitious missions beyond Earth. The successful deployment of this technology could redefine humanity's capabilities for interplanetary travel and exploration. The implementation of NASA's Nuclear Thermal Propulsion NTP engine is aimed for completion by Q4 2025, structured around 5 key phases: design validation, prototype development, testing, and safety assessments, with a budget allocation of $10 million for these initiatives. This timeline outlines the critical steps and financial planning necessary for the successful deployment of NTP technology, which is expected to enhance space exploration capabilities significantly. 1. Phase overview and budget allocation. The project is divided into 5 distinct phases, each focusing on different aspects of development and testing. The initial phase centers on design validation, ensuring that the theoretical designs align with practical capabilities. Following this, prototype development will take place, where physical models of the engine will be created and tested. The testing phase will involve rigorous evaluations to ascertain performance metrics and safety standards. Importantly, a budget of $10 million has been earmarked for these activities, emphasizing the project's commitment to thorough safety assessments and prototype development to mitigate risks associated with nuclear technologies. 2. Integration of information from various sources. The project's timeline aligns with NASA's broader strategic goals of advancing propulsion technologies for deep space missions, including missions to Mars and beyond. The NTP system is expected to provide a higher specific impulse compared to conventional chemical rockets, allowing for faster travel times and greater payload capacities. This integration of advanced propulsion systems is crucial for future exploration initiatives, as highlighted in multiple strategic documents from NASA. 3. Common key points across various sources. Several key points emerge regarding the NTP project. Safety and risk management. Emphasis on safety assessments is recurrent, reflecting the inherent risks of using nuclear technology in space exploration. Technological advancements. The potential for NTP to revolutionize space travel is consistently acknowledged, with projections indicating reduced travel times to Mars. Budget constraints and allocation. The specified budget of $10 million indicates a focused financial strategy, underscoring the importance of resource allocation in achieving project milestones. 4. The differences between sources. While most sources agree on the general timeline and phases, some provide varying details on specific technologies involved and the anticipated challenges. For instance, some sources highlight the importance of materials science advancements necessary for the engine's construction, while others focus on the regulatory aspects of using nuclear technology in space. 5. Timeline of events. Q1 2023, design validation phase begins. Focusing on ensuring that the proposed designs meet the necessary specifications and safety standards. Q3 2023, completion of design validation leading into prototype development. Q2 2024, development of the first prototypes commences, integrating lessons learned from the design validation phase. Q4 2024, testing phase initiated where prototypes undergo rigorous performance evaluations. Q2 2025, safety assessments are conducted concurrently with testing to ensure compliance with safety regulations and operational standards. Q4 2025, target completion date for the project with the NTP engine ready for operational deployment in future missions. In conclusion, NASA's NTP initiative is positioned as a transformative step in space exploration with a clear timeline, budget, and strategic objectives laid out for successful implementation. The integration of nuclear thermal propulsion technology promises to enhance mission capabilities significantly, paving the way for more ambitious explorations of our solar system. The report regarding NASA's Nuclear Thermal Propulsion (NTP) engine implementation by Q4 2025 contains vital information that often goes unnoticed in broader discussions. Here are several critical aspects that merit attention. 1. Budget allocation for safety assessments. The earmarked budget of $10 million emphasizes the project's commitment to safety, which is a paramount concern when dealing with nuclear technologies. While many may focus on the innovative aspects of NTP, the allocation for safety assessments is significant because it illustrates a proactive approach to risk management. The public often underestimates the potential hazards associated with nuclear systems, particularly in space exploration, where the implications of failure are magnified. Ensuring rigorous safety evaluations not only protects mission success but also public perception and acceptance of nuclear technology in space. 2. Materials science innovations. The project's reliance on advancements in materials science is frequently overlooked. The development of the NTP engine requires materials that can withstand extreme conditions such as high temperatures and radiation. This aspect is crucial because the success of the NTP engine hinges not just on the propulsion mechanism but also on the materials used in its construction. Innovations in this field could lead to breakthroughs that extend beyond space exploration, impacting various industries on Earth such as aerospace, automotive, and energy sectors. The long-term significance of these advancements should not be underestimated, as they could revolutionize how we approach engineering challenges in extreme environments. 3. Integration with NASA's strategic goals. The timeline for the NTP initiative aligns with NASA's broader objectives for deep space missions, particularly to Mars. However, the impact of NTP on mission capabilities is often understated. The ability to reduce travel time to Mars enhances the feasibility of human exploration and could pave the way for sustainable colonization efforts. This potential to revolutionize human presence beyond Earth is a significant aspect that deserves more attention, as it could redefine humanity's future in space. For public perception and policy implications, the inclusion of nuclear technology in space exploration sparks public debate, often influenced by historical fears surrounding nuclear energy. The report underscores the necessity for NASA to engage in transparent communication about the safety and benefits of NTP. This is not merely a technical issue but a policy one, as public acceptance is vital for the future of nuclear technologies in space. The significance lies in the potential for this project to reshape narratives around nuclear energy, potentially leading to more supportive policies that could facilitate the use of nuclear technology in other sectors. 5. A phased approach and risk mitigation. The 5-phase approach to the NTP implementation is a strategic framework that allows for ongoing evaluation and adaptation. Each phase builds on the previous one, enabling NASA to address issues as they arise and adjust timelines or resources accordingly. The significance of this phased methodology is often overshadowed by the excitement of technological advancement. However, it exemplifies best practices in project management and risk mitigation. The structured approach can serve as a model for other complex projects, demonstrating that thorough planning and flexibility can coexist with innovation. In summary, while the report highlights NASA's ambitious timeline and objectives for the NTP engine, several crucial aspects are often overlooked. The focus on safety assessments, material science innovations, alignment with strategic goals, public perception management, and the phased implementation approach all play significant roles in the project's success. Recognizing these components is essential for a comprehensive understanding of the potential implications of the NTP initiative, both for space exploration and broader technological advancements. 1. Project phases and budget allocation. The implementation of NASA's Nuclear Thermal Propulsion (NTP) engine is structured into 5 critical phases: design, validation, prototype development, testing, safety assessments, and final deployment. Each phase is essential for ensuring that the project adheres to the required specifications and safety standards. With a budget of $10 million allocated specifically for prototype development and safety assessments, this financial planning reflects a commitment to thorough risk management, which is especially crucial when dealing with nuclear technology and space exploration. 2. Integration with NASA's strategic goals. The NTP project aligns with NASA's broader strategic objectives aimed at enhancing propulsion technologies for deep space missions. The anticipated higher specific impulse of the NTP engine will allow for faster travel times and greater payload capacities, making it a game-changer for future missions to Mars and beyond. This integration is vital for fostering advancements in space exploration capabilities as outlined in various NASA strategic documents. 3. Safety and risk management. Safety assessments are a recurring theme in discussions about the NTP project, emphasizing the inherent risks associated with nuclear technology. Given the complexities of using nuclear propulsion in space travel, rigorous safety assessments are necessary to mitigate potential risks. This focus on safety is not only critical for the success of the NTP engine but also for maintaining public trust in NASA's capability to handle nuclear technology responsibly. For the technological advancements and challenges, the NTP project is seen as a potential revolution in space travel, particularly for missions to Mars. The discussions surrounding the project highlight both the technological advancements expected from NTP and the challenges that may arise. Variations in sources indicate differing perspectives on the technologies involved and the anticipated challenges, such as material science advancements necessary for engine construction and the regulatory hurdles related to nuclear technology in space. Understanding these challenges is essential for navigating the complexities of developing and deploying the NTP engine successfully. In summary, the implementation of NASA's NTP engine by Q4 2025 represents a significant step toward revolutionizing space exploration. Driven by structured phases, a strategic alignment with broader goals, a strong focus on safety, and the management of technological challenges. Here are 3 famous historical cases that align with the implementation of NASA's Nuclear Thermal Propulsion (NTP) engine technology. 1. Project Orion, 1950s to 1960s. Project Orion was an early American project aimed at developing a spacecraft propelled by nuclear pulse propulsion. The concept involved detonating nuclear bombs behind a spacecraft to propel it forward, theoretically allowing for rapid travel through space. This ambitious project was initially driven by the potential for interplanetary travel, particularly to Mars. Although it never reached fruition due to various technical, political, and safety concerns, the research and development efforts laid foundational ideas for later propulsion technologies, including nuclear thermal propulsion. The project faced significant challenges in terms of safety assessments and public perception of using nuclear devices for propulsion. Similar to the contemporary concerns surrounding NASA's NTP engine and its safety protocols. 2. Nuclear rocket development NERVA 1960s. The Nuclear Engine for Rocket Vehicle Application NERVA program was a NASA initiative that successfully demonstrated nuclear thermal rocket technology during the 1960s. NERVA aimed to create a nuclear thermal rocket engine that used uranium as fuel, which would heat a propellant, usually hydrogen, to produce thrust. The program successfully tested several prototypes demonstrating the feasibility of nuclear thermal propulsion for future space missions. However, like the NTP program, NERVA faced budget constraints and shifting political priorities that ultimately led to its cancellation. The lessons learned from NERVA regarding design validation, performance testing, and safety assessments are directly applicable to the current NTP initiatives. 3. The Space Shuttle Program 1981 to 2011. The Space Shuttle program, operated by NASA, is a prime example of the complexities of developing and implementing advanced aerospace technologies. The program underwent extensive design validation testing and safety assessments before its operational deployment. The challenges faced, including the tragic Challenger and Columbia disasters, highlighted the critical importance of rigorous safety protocols and comprehensive testing methodologies in aerospace projects. The NTP engine initiative mirrors this historical context, emphasizing the need for thorough safety assessments and prototype testing to ensure the reliability and safety of nuclear propulsion technology in future space exploration missions. These historical cases not only provide context for the development of NASA's NTP engine but also illustrate the ongoing challenges and considerations associated with advanced propulsion technologies in space exploration. Future outlook. Implementation of NASA's Nuclear Thermal Propulsion NTP engine by Q4 2025. As NASA aims to implement its Nuclear Thermal Propulsion NTP engine by Q4 2025, the future of space exploration is set to take a transformative leap. This ambitious project, structured around 5 key phases: design validation, prototype development, testing, and safety assessments, promises to significantly enhance our capabilities for deep space missions, including potential manned missions to Mars and beyond. Here are predictions and future implications surrounding this critical project. 1. Revolutionizing space travel. The successful deployment of NTP technology is expected to drastically reduce travel times for deep space missions. Currently, conventional chemical propulsion systems limit the speed and payload capacity of spacecraft. With NTP engines offering a higher, specific impulse missions to Mars could see travel times slashed from several months to just weeks. This acceleration could open new avenues for exploration, enabling more frequent missions and the potential for establishing a human presence on Mars sooner than previously anticipated. 2. Strategic global partnerships. As the NTP project progresses, NASA is likely to strengthen international collaborations with space agencies and commercial partners. Countries like the European Space Agency (ESA) and private companies such as SpaceX may see increased engagement in joint missions utilizing the NTP technology. Collaborative efforts could focus on shared research, technological advancements, and logistical support, fostering a more unified global approach to space exploration. 3. Advancements in material science and safety protocols. The development of the NTP engine will necessitate significant advancements in materials science, particularly regarding the construction of reactor components that can withstand extreme conditions. Innovations in materials capable of enduring high temperatures and radiation will likely spill over into other industries, including energy and transportation. Furthermore, the rigorous safety assessments and testing phases will set new standards for nuclear technologies, influencing regulatory frameworks and safety protocols across various sectors. 4. Public perception and policy changes. The incorporation of nuclear technology into space exploration may evoke mixed public reactions. While the potential benefits are substantial, concerns regarding safety and environmental impacts will need to be addressed proactively. As NASA conducts its safety assessments, transparent communication will be essential to build public trust. Policymakers may also need to adapt regulations surrounding nuclear technologies in space, potentially leading to more comprehensive frameworks governing the use of nuclear energy beyond Earth. 5. Inspiration for future generations. The NTP initiative has the potential to inspire a new generation of scientists, engineers, and explorers. As the project progresses, educational outreach and STEM science, technology, engineering, and mathematics initiatives could leverage the excitement surrounding nuclear propulsion to foster interest in space science. This could lead to increased enrollment in related academic fields and a workforce better equipped to tackle future challenges in space exploration and technology development. Conclusion. The implementation of NASA's Nuclear Thermal Propulsion Engine by Q4 2025 represents a pivotal moment in space exploration history. As we look forward to the successful execution of this project, the implications extend far beyond immediate technical capabilities. The advancements in propulsion technology, international collaborations, material science, regulatory policies, and public engagement will shape the future landscape of space exploration, marking a new era of human discovery and innovation. The vision of exploring Mars and beyond seems increasingly attainable, with the potential to redefine humanity's role in the cosmos.